Hey there. Last time, we played with benchmark.net and saw how great it is for testing raw C# performance. I love it and I use it all the time. But when you need to measure how your actual game behaves, benchmark.net just doesn't cut it. You need real numbers on a real build running on a real device. Sure, you could hack something together with a stopwatch, but there's a better way. I'm talking about Unity's performance testing framework, which is built on top of Unity's test runner. I've already made 2 videos about unit testing in Unity, and while you don't need to watch those to follow along with this video, if you want to understand the test runner in more depth, I'll link them in the description. I'm not sure from which Unity version the performance testing framework is installed by default as a dependency, but to make sure it's installed or to install it if you don't have it, navigate to the Package Manager, then Unity Registry, and search for Performance Testing API. Mine is already installed, and I can't even delete it because it's a dependency. If yours is not, you'll see the Install button here. Now I need to create an editor test assembly. This is the same process I covered in my unit testing videos, so I won't go into too much details here. I'll create a new folder called Tests, create an assembly via Test Runner window, and name it something like Performance Tests. One last thing. In order to use the performance testing package in this assembly, I have to reference it. Just search for performance testing and select it. Great, now we're ready to write our first performance test. The performance test I'm going to implement here was covered in detail in my previous video, so I won't go into much detail on how it works or what it tests. I'll leave the links for the videos in the description. They cover all of that and much more. A quick disclaimer I should have probably mentioned in my original 4 verses for each video. You'll almost never need to optimize this hard in real projects, but exploring it is super useful for understanding how the C# compiler actually behaves. First, I'll create the benchmark class, and I'll add a private field to hold the array. Now let's create our first test method. I'll call it forLoop, and it'll take an int parameter for the collection size. Inside, I'll initialize the array with a range of numbers, and then comes the interesting part, the measure method call. This is how we tell Unity what to measure. I'll pass it a lambda that does the actual work, declaring a sum variable and iterating through the array with a for loop, adding each element to the sum. Now, I can configure this test. The configuration uses the factory pattern along with Fluent API styles, so I can chain the configuration methods one by one. Let me walk through each one because they're important. First, sample group. By default, Unity measures in milliseconds, but that's way too large for what we're testing. So I'm creating a sample group with a custom name and specifying microseconds as the unit. I'm also including the collection size in the name. This will help me if I'll want to bring my results to some external analysis tool. Next, warm-up count. This is how many iterations to run without measuring. I talked about this in my benchmarking videos. Warm-up runs are crucial because they let the JIT compiler optimize the code and get the CPU cache warmed up. I'm setting it to 10. Then we have measurement count. This is how many times we actually measure the performance. The framework will calculate the median from all these measurements. And here's the important part, iterations per measurement. If we specify a number, let's say 10, the results will be the total time for those 10 iterations, not per iteration. So you'll have to manually divide all results by 10 to know how much time your code actually took. If we forget to specify this value, Unity defaults to running as many iterations as it can fit in 1 millisecond. So I'm explicitly setting it to 1, meaning measure the code in the lambda only once, multiplied by the measurement count. Finally, we call run to execute the test. Now I need to add the attributes. I'll add test to mark this as a test method and performance to mark it as a performance test specifically. Then I'll add 3 test case attributes with different collection sizes, 10,000, 100,000, and 1 million. In case you haven't watched the unit test videos, the test case attribute tells the test framework to run this test with a specific parameter. So this test will run 3 times, 1 for each number I specified. Now I'm going to paste 2 more test methods here. One for an optimized for loop and one for each. And I feel like a broken record here, but if you want to know what's so optimized about this for loop, I have a video on this where I explain everything in depth. Alright, we've got 3 test methods, each with 3 test cases. Let's see how to run them. In the test runner window, we can see all of the tests I just created as if there were unit tests. Let me run all of them and wait for them to finish. You can see that each test method shows 3 results, 1 for each collection size. Let me expand one. Here's what Unity shows us. The sample group name we configured, the unit we're measuring in, microseconds, and 3 important numbers, minimum, median, and maximum execution time. The median is what we care about most. It represents the typical performance, filtering out outliers from both ends. If I scroll down, there's this massive JSON output. This is the raw data from all measurements. When executing the tests from the test runner, the results are stored in memory. But if you run the tests from the command line, you can specify a destination file. Or you can export it with a custom editor script. Now, looking at results like this is not great. There's a better way. Let me open the Performance Test Report window from Window, General, Performance Test Report. This gives a much nicer visualization. We can see all our tests, compare them side by side, and the data is much easier to digest. We can also view a simple graph of measurements. Here's something I miss in this framework. There is no good way to group tests. Everything is just listed under the class name. In benchmark.net, we could group by collection size, secondary measurements, and easily compare all 3 loop types for each size. Here, not so much. The good news are, while this report viewer is pretty basic, if you want serious data analysis, like trends over time, statistical significance, proper visualization, you can export the JSON and use your own tools. Or build a custom viewer inside Unity. And honestly, if anyone in the audience has built something like that, please share a link in the comments. I'd love to see it. In benchmark.net, we could measure memory allocations alongside execution time. Naturally, we'd want to do the same here. You might think, okay, let's just add GC measurement. I'll modify the for each test and chain in a GC call. Just like in benchmark.net, it adds a secondary measurement. But it's not measuring what we want. It's counting how many times garbage collection occurred during the test, which is not the same as how much memory we allocated. Unfortunately, with this framework, we can't measure low-resolution allocations. The thing is, Unity's managed heap grows and shrinks in chunks. So while you can create measurements using the profiler or GC classes, you won't see results per allocation if the allocation is small enough. Which again, in most real-life scenarios is not that important and we can really work with what we have here. Let me show you what I mean. I'll create a new test class called Allocation Benchmark. First, a new sample group. I'll call it GC and I'm specifying that my measurements are in bytes. Then I'll create multiple measurements. So I'll create a for loop with 100 iterations. Inside it, I'm measuring current heap usage with Unity's profiler.getMonoUsedSizeLong method. Then I allocate an array with the provided size and measure the difference in allocated memory between the current value and the value I got before allocating the array. And lastly, I'm recording a custom measurement by using the sample group and the result I got. Now it's time to mark this method as a performance test and provide test cases. I'll go with a couple of sizes and I'm not using power of 2 numbers on purpose. There is another approach to measure the memory. I'll copy this method, change its name, and now I'll change the measurement call. Instead of using Unity's profiler class, I'll use GC getTotalMemory here. In most cases, both of those methods will report the same value. Now, let's break down the expectations. Theoretically, if we allocate 2-byte array, we should see 2 bytes of allocation, plus somewhere between 4 and 24 bytes for the array object itself, depending on the platform, plus some alignment. But I wouldn't expect more than 32 bytes in total. And the similar pattern is expected with other small numbers. When we reach higher numbers, the alignment and padding should affect the results less. Now, let's see what we're actually getting. It's not a mandatory step because the data will be overridden, but I'll clear the results from the test report window manually. Now, let's run the newly created tests. And look at this! The tests with 2, 4, 10, 100, and 1000 bytes, they're reporting 0 allocations. Only the 10,000 byte test shows allocations. And all of them, both the Profiler and GC versions, report exactly 12,288 bytes. That's strange. But wait, does that number look familiar? It's actually 4096 times 3, exactly 12 kilobytes. Unity allocates memory in blocks. I was unable to find the exact sizes, but from my tests for smaller allocations, the blocks are always the size of 4 kilobytes. So here's what's happening. If Unity's current memory consumption is at 4096 bytes and we want to allocate one more byte, Unity reserves another 4096 byte block, and it reports that full block as allocated. If we'll allocate more memory within the current block, Unity doesn't report any new allocations because the memory was already reserved. That's why our smaller test showed 0 allocations. Unity had already allocated memory, and we had spare space within the current block. In fact, if we take a look at the data for the 2-byte test case, we can see that there is one allocation of 4 kilobytes there. But in the summary, it got stripped as an outlier since 99 other measurements reported 0. This can be helpful if you want to know how much total memory your game consumes, but it won't help you understand how much work the CPU has to do with garbage collection. Because the garbage collector doesn't really care about empty reserved memory, it only cares about the actual objects. But again, it's only 4 kilobytes, you shouldn't worry about it. I bet you have bigger issues. We'll see this more clearly in a real build. And here's one of the biggest benefits of Unity's performance testing framework. You can run performance tests in real builds, including IL2CPP. And it's pretty easy, at least with Mac or PC builds. It's a bit harder with mobile, but still possible. To run on desktop though, I just need to switch to the Player tab in the Test Runner window and… wait a second. Up until now, we've worked on edit mode tests. And once again, I'll leave a reference to my unit test video here. In order to run those tests in a build, we need play mode tests. Fortunately, it's really easy to convert edit mode tests to play mode tests. All we have to do is modify the assembly definition file. I need to remove the reference to Unity Editor and uncheck the Editor checkbox, effectively telling Unity that this assembly should be included in all builds. You can see that my tests appeared under the Player tab in the Test Runner. They are also visible in the Play Mode tab, but no longer visible in the Edit Mode tab. So, to run on desktop, I just need to switch to the Player tab and run the tests from here. This will trigger a build, execute it, measure the performance, and report everything back to the editor. Since it's building the entire game, it'll take a few minutes, so I'll speed up a little. Alright, the build finished and the tests ran. Let's see what we have. And look at the results now. The 2, 4, and 10-byte tests still show 0 allocations. With the 100-byte array, we see a couple of 4-kilobyte allocations. This means that at this point we've reached the limit of the previously allocated memory and needed one more block. For the 1000-byte test, we're seeing 4-kilobyte allocations roughly every 3 runs, and with 10,000 bytes, every single iteration allocates 12 kilobytes. The performance testing framework brings a lot to the table. Easy test execution on real builds, native Unity integration, Fluent API, and structured data output. The best use case? Integration into your CI/CD pipeline, let's say to measure how new features impact your game's performance. And by the way, let me know in the comment section if you'd want to see a video on CI/CD. I'll leave links to the documentation and code in the description. Keep on creating, and I'll see you in the next one.